In last lecture, we have discussed with operations on multiple random variables. In that one, we are having the moment about your origin and moment about your mean. Moment about your origin, it will give second order moment, that is M11. This is equal to expected value of xy. This is nothing but correlation function, which stands for capital R xy. So for this correlation function, expected value of xy, we are having the two possibilities. Either this function is equal to 0, then we can say that x and y, these two random variables, are orthogonal to each other, or they are perpendicular to each other. Second possibility, that is expected value of xy correlation function is equal to expected value of x into expected value of y. In that case, we can say that these two events or two random variables x and y, they are statistically independent to each other. When two random variables are statistically independent to each other, then we can say that these two random variables are uncorrelated to each other. Correlation, that means we are finding the similarity between these two random variables x and y. When they are totally independent, then we are not able to find out the similarity between them. Then after, we have to see the moments of two random variables about mean. In that case, we have to see second order moment, which will give us, indicated by your mu 20, then mu 02 and mu 11. So here mu 02 is nothing but expected value of x minus x bar square. This is nothing but variance of random variable x. Similarly, this mu 02, it is nothing but expected value of random variable y minus its mean y bar square is equal to sigma y square. That is the variance for second random variable y. Similarly, for this third case, we can say that this is nothing but expected value of x minus x bar into y minus y bar. So this is called as covariance of random variables x and y. This is indicated by C of xy, that is equal to expected value of x minus x bar into y minus y bar. Here xy, just do the multiplication with these two bracket terms, xy minus x into y bar minus x bar into y plus x bar into y bar. So we will get here expected value of xy minus expected value of your x. This y bar is nothing but expected value of your y minus x bar is nothing but expected value of your x. So this is expected value of x into expected value of y. We are operating this expected operator on this random variable y. So it becomes expected value of y plus x bar into y bar. X bar is nothing but expected value of x into expected value of y. So we will get expected value of xy minus or plus expected value of x into expected value of y. So we can say that covariance or the two random variables x and y, that is equal to expected value of xy minus expected value of x into expected value of y. Is it clear? Covariance between two random variables, that is equal to expected value of xy minus expected value of x into expected value of y. Here expected value of xy, what is this quantity? Yes, this is nothing but rxy minus expected value of x into expected value of y. So correlation function, that is equal to covariance function, that is equal to correlation function minus expected value of x into expected value of y. So over this one, this autocorrelation function, this correlation function or this xy, either it is equal to 0 or it will take the value, that is expected value of x into expected value of y. When correlation function is equal to 0, then we can see that these two random variables are orthogonal to each other, or they are perpendicular to each other. When we put this condition here, the covariance of two random variables which are perpendicular to each other, this will give minus expected value of x into expected value of y. They will give the similarity but in negative manner, minus. When these two random variables are statistically independent, occurrence of first random variable doesn't depend on occurrence of second random variable, they are totally independent, then we can say that these two random variables are statistically independent. So in that case we will get this correlation function xy, that is equal to 0. In last lecture we have put a star mark. One statement is given, when these two random variables are statistically independent, then these two random variables are uncorrelated to each other. Here the covariance, that is cxy, is equal to 0, then we can say that x and y are uncorrelated to each other. They are uncorrelated to each other. The reverse statement, when two random variables are uncorrelated to each other, then it is not always true, that is these two random variables are statistically independent. But when two random variables are statistically independent, it is always true that two random variables are uncorrelated to each other. We are having correlation coefficient, which is given as rho, that is equal to mu 1 1 divided by root mu 2 0 into mu 0 2, that is equal to cxy sigma x into sigma y, and this coefficient is ranging between -1 to 1. This rho stands for correlation coefficient. Correlation coefficient. Write down one example which will explore what is this statistically independent. This is the important concept. So we have to select a card from 52 playing cards, where capital A is the event select a king from the set of 52 playing cards. Repeaters करतोय. From the set of 52 playing cards, we have to select first A event, select a king. B, that is select a jack or queen, and C is the event select a heart. So first event select a king, we are having the 4 kings, so we will get probability of A, that is equal to 4 by 52. Select a jack or queen, probability of B, that is equal to 8 by 52, and select a heart, that is probability of C is equal to 32 by 52. Then find out the intersection between these two events. Probability of A intersection with B. Probability of A intersection with B, 0. Then probability of A intersection with C, 1 by 52. Probability of B intersection with C, that is 2 by 52. When I select the example related to playing cards, all are happy. Now here we are having the 3 events A, B, C. Or this one we have to find out whether they are orthogonal to each other or they are statistically independent. Yes, find out of these 3 events which are the events are statistically independent to each other. I got it? A and B are orthogonal to each other. But about statistical independent, A and C they are statistically independent. And similarly B and C, are they statistically independent? Probability of B intersection with C, that is equal to 2 by 52. We have to find out probability of B into probability of C, that is equal to 2 by 52. So here probability of B intersection C, that is equal to probability of B into probability of C. That means these 2 events doesn't depend on each other. So these 2 events are statistically independent. As these 2 events are statistically independent, we can say that their covariance is equal to 0. So these 2 events are uncorrelated to each other. Yes. Orthogonally independent? 2 events are statistically independent. See here, when we are having A intersection B, that is equal to 0, then we can say that they are mutually exclusive. Their intersection is totally 0. That means A and B are orthogonal to each other. Orthogonal to each other, or they are perpendicular to each other. There is no projection from event B to A and A to B. This is the first case. And second one, we are having probability of A intersection B, that is equal to probability of A into probability of B. From conditional probability we can say that this probability of A intersection with B, that is equal to probability of A provided B should be occur into probability of B. When two events are statistically independent, then this case occur. That is probability of A into probability of B. See, difference between these two statements. Here probability of A will occur provided B should be occurred, already occurred. Occurrence of event A is totally depend on occurrence of event B. So we will get difference between these two events. First one, probability of A intersection B, that is equal to 0. Common point or intersection point is totally 0. They are mutually exclusive. But in second case, we are having some common part is present. Some common part is present, but these two events doesn't depend on each other. That's why they are statistically independent. Is it clear? Yes or no? Can I repeat? Can I repeat? तुमच्या रिअल लाईफ मध्ये एक एक्झाम्पल घ्या. हॉस्टेलमध्ये दोन केसेस, एका रूम मध्ये राहणारे दोन मित्र किंवा आजूबाजूच्या रूम मध्ये राहणारे दोन मित्र. ह्या दोघांमध्ये कॉमन पार्ट काहीच नसतो. देअर इंटरसेक्शन इज 0. बट इन सम केसेस एका रूम मध्ये दोघ जण राहत आहेत. रूम दोघांची एकच आहे, कॉमन रूम आहे, पण दोघांचं एकमेकाशी पटत नाहीये. इन दॅट केस दे आर स्टॅटिस्टिकली इंडिपेंडेंट. तो उठला काय नाही उठला काय मला काही घेणं नाही, कॉलेजला गेला काय किंवा नाही गेला काय मला काही घेणं नाही. बट ज्यावेळेस दुसरा मित्र असेल, तो उठल्यानंतरच आम्ही दोघ जण सोबत निघतोय कॉलेजला. त्याचा नाश्ता झाल्यानंतरच मी पुढे जातोय किंवा माझा नाश्ता झाल्यानंतर आम्ही दोघ जण मिळून जातोय. इन दॅट केस वी कॅन से दॅट दे आर नॉट स्टॅटिस्टिकली इंडिपेंडेंट. पण एकाच रूम मध्ये राहतोय, दोघांचं एकमेकाशी काहीच पटत नाहीये. पटत नाही म्हणण्यापेक्षा डिपेंडन्सी काहीच नाहीये. तो समजा आर्ट फॅकल्टीचा आहे, मी सायन्स फॅकल्टीचा आहे, इंजिनिअरिंगचा आहे. दोघांचं काहीच घेणं देणं नाही. इन दॅट केस युअर इंटरसेक्शन इज प्रेझेंट but dependency 0. Same case, we are having two events A and B. When these two events are dependent on each other, then we will get this case, that is probability of A intersection B, that is equal to probability of A, B is already occurred, into probability of B, or we can say that probability of A into probability of B provided A should be occurred. Conditional intersection. In this case, probability of A intersection B, that is equal to probability of A into probability of B. These are totally independent. These two events their occurrence doesn't depend on occurrence of other events. Totally independent. That's why this is called as statistical independent. When these two events are statistically independent, we can say that we are having covariance, that is equal to expected value of xy minus expected value of x into expected value of y. Covariance, when these two events it is equal to expected value of x into expected value of y, we will get this covariance function that is equal to 0. When covariance function is equal to 0, we can see that these two random variables x and y, they are uncorrelated to each other. When two random variables are statistically independent, their correlation or covariance is equal to 0, then we can say that these two random variables are uncorrelated to each other. And first case, intersection is 0, mutually exclusive. Their common part is 0. They are totally exclusive. Is it clear? Write down one example regarding this one. Two random variables x and y. Consider two random variables x and y with joint probability mass function, that is capital PMF. Probability mass function capital PMF, which is given as P of xy or x comma y, which is given as x1 is equal to 1, x2 is equal to 0 and x3 is equal to 1. We will get y1 is equal to 0, y2 is equal to 1. Zero, 1 by 3, 0, 1 by 3, 0 and for this one we have to find out whether these two random variables x and y are correlated to each other or they are statistically independent. So over this any event you have to calculate their joint probability distribution. So over this one, yes, we have to consider or xy for x is equal to 0 and y is equal to 1. X is equal to 0, this. Y is equal to 1, this one. This probability, that is joint probability, is given as 0. Here we will get joint probability is equal to 0. Now we have to find out the marginal probability. So marginal probability for y is equal to 1, we will get 1 by 3 plus 1 by 3, it will give 2 by 3. Marginal probability for y is equal to 1, 1 by 3 plus 1 by 3, we will get 2 by 3. Here y is equal to 0, marginal probability is 1 by 3. For this case, x is equal to 1, marginal probability for x is equal to 1, it is 1 by 3, here 1 by 3, 1 by 3. Now for total probability, just add this one. We will get total probability is equal to 1. Here total probability is equal to 1. Now first of all you have to check whether these two random variables, their correlation function, that is correlation function is given as Rxy, that is equal to expected value of x into expected value of y. Or here for the probability you have to check this probability for probability of x is equal to 0 into probability of y is equal to 1. Probability of x is equal to 0, this is the marginal probability. Marginal probability for x is equal to 0, which is given as 1 by 3. Multiplied with probability of y is equal to 1, 2 by 3. This will give 2 by 9. So here we will get the joint probability for this event, x is equal to 0 and y is equal to 1, that is equal to 0. That is not equal to probability of x is equal to 0 into probability of y is equal to 1. What is the conclusion? These two random variables are not statistically independent. They are dependent on each other. Write down this statement. X and y, for these two events, x is equal to 0 and y is equal to 1. These two random variables are dependent on each other. Then we have to find out their correlation, covariance covariance of xy, that is equal to expected value of xy minus expected value of x into expected value of y. Just find out expected value of x, expected value of y. Value of x, which is given as 1 into 1 by 3 plus 0 into 1 by 3, and here 1 into 1 by 3. Here x is minus 1. Minus 1 into, so here covariance, that is equal to expected value of xy minus expected value of x into expected value of y. We have to calculate the mean value for x random variable and also for mean value for random variable y. So here for x random variable, this first is x1 is equal to minus 1, x2 is equal to 0 and x3 is equal to 1. Minus 1 into 1 by 3 plus 0 into 1 by 3 plus 1 into 1 by 3. This will give the mean value, that is equal to 0. Similarly, for random variable y, y bar is equal to 0 into its marginal probability into 1 by 3 plus 1 into 2 by 3, that is equal to 2 by 3. In this way we will get mean value for x and y. Similarly, you have to calculate expected value of xy. This will give the joint probability. Here we have to consider joint probability. For this case, we have to consider, I will get only 3 points where joint probability is present. So just calculate. X is equal to minus 1, that is xy bar, which is given as x is equal to minus 1 into y is equal to 1 into their joint probability 1 by 3 plus x is equal to 0, then y is equal to 0, their joint probability 1 by 3 plus x is equal to 1, y is equal to 1, their joint probability 1 by 3. Is it clear to all of you? We have to calculate the joint probability. Mean value for your joint probability, which is given as expected value of xy, that is xy bar, which is given as, here we will get these 3 probabilities. So that's why I have calculated this one. X is equal to minus 1, y is equal to 1 by 3. Here x is equal to 0 and y is equal to 0, 0 into 1 by 3 plus x is equal to 1, y is equal to 1 by 3. So this value becomes 0, this is 1 by 3, so this is equal to 0. It is equal to 0. So here we will get expected value of xy is equal to 0 minus expected value of x into expected value of y. Here expected value of x, that is x bar, which is given as 0 into expected value of y, which is given as 2 by 3. So we will get 0. So here your covariance is equal to 0. So we can say that x and y are uncorrelated to each other. These 2 random variables x and y, they are uncorrelated to each other because we will get the covariance that is equal to 0. And here for first case we have to calculate probability, joint probability for x is equal to 0, y is equal to 1, that is equal to 0. Their marginal probability for x is equal to 0, we will get 1 by 3, and y is equal to 1, x is equal to Is it first case? Minus 1. Here x is equal to 0, y is equal to 1, 0. Then we have to find out the marginal probability for x is equal to 0, which is given as 1 by 3, and for y is equal to 1, 2 by 3, that is equal to 2 by 9. So we will get probability, joint probability for x is equal to 0, y is equal to 1, that is not equal to probability of x is equal to 0 into probability of y is equal to 1. So here x and y are dependent random variables. They are dependent to each other. This is the justification for your second statement. When these two random variables are uncorrelated to each other, it is not always true that is these two random variables are independent to each other. This is the justification for second statement. Is it clear to all of you? Just cross verify the dependence of this random variable. You have to take any event. Just find out for this x is equal to minus 1 and y is equal to 1 by 3. For this event, we have to find out whether these two random variables are dependent on each other or independent. So here we will get their joint probability, that is equal to probability, here probability, joint probability for x is equal to minus 1 and y is equal to 1, that is given as 1 by 3. Their marginal probability for x is equal to minus 1, 1 by 3, for y is equal to 2 by 3. Is it equal? No, that is not equal to probability for x is equal to minus 1 and for probability of y is equal to 1. You have to cross verify for any event. Then when this is true for all the events, then we can say that these two random variables are dependent on each other, and from this statement their covariance is equal to 0. We can say that x and y are uncorrelated to each other. Then write down your second example from your favorite, that is tossing a coin 3 times. We are having the joint probability distribution function for these two random variables, x, which will take the values minus 3, minus 1, so from your previous example we are having the x is a random variable which will take the values minus 3, minus 1, 1 and 3. Y is a random variable which will take the values 0, 1, 2 and 3. So over this one we have to find out the joint probability distribution. So here we will get 1 by 8, 0, 0, 0. Total probability is 1 by 8, 0, 3 by 8, 0, 0, 3 by 8, then 0, 1 by 8, 2 by 8, 0, 3 by 8, then 0, 0, 0, 1 by 8, this is 1 by 8, total probability is 1. Marginal probability here 1 by 8, 4 by 8, 2 by 8 and 1 by 8. This is the joint distribution, joint probability distribution for these two random variables. Over this one we have to find out whether these two random variables are dependent or independent to each other and whether they are correlated or uncorrelated to each other. So first step, you have to find out their dependency. So here assume you have to consider any joint probability density function. So for first case we have to consider probability for x is equal to minus 3 and y is equal to 0. This joint probability is given as 1 by 8. So probability for x is equal to minus 3, marginal probability for x is equal to minus 3, 1 by 8, and probability for y is equal to 0, 1 by 8. So here we will get probability of x is equal to minus 3 and probability of y is equal to 0, that is equal to 2 by 8, which is not equal to. One by here we can say that joint probability for these two events x is equal to minus 3 and y is equal to 0, which is not equal to probability of x is equal to minus 3 into probability of y is equal to 0. So from this statement we can say that x and y are dependent random variables. You have to cross verify with other events. Just verify for x is equal to 1 and y is equal to 2. The joint probability x is equal to 1, y is equal to 2, 2 by 8. Marginal probability x is equal to 1, 3 by 8 multiplied with 2 by 8. So these are not equal to, that is 6 by 64. So we can say that x and y, they are dependent random variables. Now for whether they are correlated or uncorrelated to each other, we have to find out the covariance, that is equal to expected value of xy minus expected value of x into expected value of y. Just find out the mean for random variable x, mean for random variable y. Mean for random variable x, here you will get marginal probability 1 by 8, 3 by 8, 3 by 8, 1 by 8. So for mean minus 3 into 1 by 8 plus minus 1 into 3 by 8 plus 1 into 3 by 8 plus 3 into 1 by 8. This will give the mean value for random variable x. Into 1 by 8 plus 1 into 4 by 8 plus 2 into 2 by 8 plus 3 into 1 by 8. This will give the mean value for random variable y, which is already calculated in your previous lectures. That is 1.375. Is it clear? Similarly, we have to calculate the expected value of xy. We have to find out the mean for these two random variables. Joint mean, that is expected value of xy, which is given as x by bar. X by bar. So here we will get probability at this point, this point, this point, this point. So we have to calculate minus 3 into 0 into 1 by 8 xy bar, joint probability distribution. See here, all of you. To find out the dependency, we are having the two ways. First of all, we have to check their joint probability, and final way, we have to find out their correlation and mean value. Just equate when this correlation function, that is expected value of xy is equal to expected value of x into expected value of y, then these two random variables are uncorrelated to each other, or we can say that these are statistically independent. Is it clear? Any questions?